And I'm going to go over to look at the chapter 3 in the ebook. So here is chapter 3 in the ebook. And it starts out with this little commentary about the law school aptitude test, admissions test. They have lots of logic questions in that. It's all like verbal reasoning. If you imagine the Venn diagrams that we were doing, it's like there's all these categories of undesirable human behavior, with overlaps. So one thing might count as more than one different crime, or some crimes are a subset of the other crime. And so there are all these reasoning problems that they give you, to figure out what categories does this belong to. And all right, so section 3.1, it's got the usual paragraph about the history at the beginning. And so logic started out as a branch of philosophy, and it wasn't really connected with mathematics at the beginning. And what Leibniz had a vision, a dream, a goal. What he wanted to do was to create a language where the grammar would prevent you from saying anything false. Okay, where a false statement would be an ungrammatical statement. Now he did not achieve that. Okay, but he did get started with the idea of writing down the formal rules for, when does one statement follow from another. And I had a friend who had sort of looked into this a little bit, who was of the opinion that before Leibniz, like looking in like the 15th century, the 14th century, that the reasoning was really bad. That if you would read these arguments, and by modern standards, you'd say that does not follow, So maybe Leibniz improved things a little bit. And then we've seen De Morgan already with his rules about intersections of sets. We had De Morgan's laws in chapter 2. And the next piece of it is George Boole with the Boolean Algebra, where he came up with a symbolic notation for logical propositions, logical statements, and create a way where you can simplify expressions like you did in your algebra class, where the variables stood for numbers. And simplifying logical expressions, it's an important thing for designing electronic circuits, to do the reasoning with the fewest possible steps. So it's an algebraic simplification of a statement. All that will make more sense after we really do the chapter. So the last person mentioned here is Bertrand Russell. Here they just mentioned him because of his comment on Boole, but he was writing in the 1920s, and he wrote a book called Principia Mathematica, fancy Latin way to say principles of math. But his idea was to start way down at the foundation and build it up. He wanted to have the smallest possible number of axioms or assumptions at the beginning, and then just build up from there using logic. And so that was an influential book. And in the course of writing that, he came up with some paradoxes and took a while to sort out. So that's Bertrand Russell. All right. So chapter starts out with logic statements. As usual, our author, who looks very surprised in that picture, does a video. And so I encourage everybody to watch the author's lectures. And but what's a statement? Okay. So questions don't count, commands don't count, opinions, our author does not want to count them. Yeah, okay. But so we're talking about the kind of statement where it's a statement of fact, not necessarily true. It's a statement that could be either true or false. Doesn't matter about that. It's still a statement, even if it's false. But what makes it a statement is that if we only knew, it would definitely be either true or false, not both. Okay? So it's a statement that has a truth value whether we know the answer or not. Okay. I mean, I guess I believe them that Denver is the capital of Colorado, but honestly, I've forgotten. So either way, this is still a statement. Okay. So there's the definition, a declarative sentence that's either true or false, but not both. And you don't have to figure out whether it's true or false to figure out whether it's a statement. Okay. And then they have some exercises where you identify the statements. And, you know, A is a statement, it's a true statement. C is a statement, I'd have to check if it's true or false. D is kind of a strange animal. D is what you call an open statement. If you put in a number for X, then it would be either true or false. If you put in the right number, if you put in a 4, it's true. And if you put in anything else, it's false. So it's an open statement, but one that would have a truth value if you filled in the variable. Okay. So here's one of these paradoxes. Say, this is a false sentence. Well, you see the problem. If this is a false sentence, then it's false that it's a false sentence, which makes it a true sentence. Okay. If a true sentence, that means it's true that it's false. Okay. So this is not a statement. So it's not that everything you can say in English would qualify as a mathematical statement. You can say things that don't qualify. Okay. I think I want to digress for a minute. There's a thing just like that in set theory. Not every thing that you could write down in set builder notation actually makes a set. So let me switch the share over here to the piece of paper. Do a brief side note. So S is a set of sets. Each member of S, it's not a number, X is not a number here. Each member of S is a set. It's the collection of all the sets that do not contain themselves as a member. Question. Is S a member of itself? If it is, if S is in there, then it's not. Then if S is not one of these, then it is. Russell's paradox. So, when you write set builder notation, there's a limit on what you can do, and I'm going to tell you what that is. Whoa. This thing that goes in the box here you have to fill the box in with something that you already know is a set. So that's why I was always writing things like
Fred, we can't see what you're writing.
oh, thank you. I was always writing things like the set of X element n such that, I don't know, X bigger than 2. Yeah, I was always writing where I'd fill in here something that's already been proven to be a set. And that's what's missing up here from from Russell's thing, he's got the X element of what? Set of all sets. Set of all sets is not a set. Say, well, how would I prove something is or is not a set? Okay, well, that's complicated. You have to start with some axioms. And so there's a Zermelo-Frankel set theory. You don't have to remember the names. Different sets of axioms, 7 or 8 of them, that you start from. I say 7 or 8 of them because one of them, the axiom of choice, is an axiom that some people believe in, and some people choose to build their mathematics using it, and others choose not to use it. And axioms, you say, well, let's start with these things that don't contradict each other, and then we go from there to see what we can get by logic, by deduction. And so some people take this axiom of choice and some people do not. That I mention it. Why would I talk about this? Well, the thing we just did with Cantor, he used this axiom of choice in his argument when in the one where we showed that the set of real numbers is not countable. He said, well, we can choose, and if we make a list, we can choose a new number that's different at every decimal place. And there's an axiom involved there that you can claim to do that even, well, I'll just leave it at that. It's an axiom. You can argue about whether he could really do that. And so math can be built with or without the axiom of choice. So you either have 7 or 8 axioms, assumptions that you start with for set theory, can prove from them that there are some sets, some things are sets, like the set of natural numbers, prove from the axioms that certain things are sets. And then whenever you write this set builder notation, you just limit yourself to only talk about elements that are within something that you already know is a set. And that prevents this kind of self-contradiction that you have in Russell's paradox. And then going back to our book, you can see how there's a real similarity between this is a false sentence that contradicts itself and Russell's thing up here, where you make a definition of a set that contradicts itself. And well, I'll leave it at that. Okay. So, anybody want to, you have questions up to here, or you want to discuss that, or you want me to just say something again? Let's see, Darwin's not muted. Darwin? No?
That was an accident.
Oh, okay, no problem. See anybody else here? Okay. All right. So, which one here is a statement? Well, I'm not sure what they're going to tell you about B, but I'm going to say that's not a statement. I mean, unless well, it depends. I'd have to give you a definition of large first, If I told you okay, let large mean bigger than 10, okay. But if I don't say anything else about what large is, this is an opinion. It's not a precise term. Yeah, oh, good, they agree with me. All right. So we can't really determine. Oh, now here's a statement to C. Oh, I would love to get A show of hands, not for the political stuff. Stay away from that. But no, what I mean is, how many people? Let's use the participants window over here. If you think C is a statement, put up a yes, and if you think it's not a statement, put up a no. Oh. Okay, let's see in the window there I can see so far, I got 3 yeses, 5 no's. Well, now I know why the author put it there. Okay. Yeah, okay, it gets philosophical. But are you guys thinking this is the same kind of thing like B? So I think the author and I don't think of it that way. Okay. In this one, we don't know yet. But just because we don't know doesn't mean that it isn't definitely one or the other. The only way I can see around that is if there's ambiguity about the definition. Either is it because of age, or how, depending on the culture, how old does a person have to be counted as a woman, or does it depend on, are we talking about genetic, anatomical, or identity?
Or what about history, Fred? I mean, if we base it off of history, there's never been a woman president.
Yeah, but that doesn't bear on whether this is a statement or not. You got it? Because there's true statements and they're false statements, but they're both statements. So, whether it's going to happen or not, we don't know, but whichever way it goes, this is still a statement. It's going to be either true or false. You see what I'm saying? It's a statement that has a truth value, whether we know the truth value or not. If we agree on a definition of woman at the beginning, like we had to agree about a definition of large in the previous example. So if you've agreed on a definition, these are both statements. If you've not agreed on a definition, they're not statements. And I actually do not know which way the author goes on this. This author may or may not believe that the word woman is an unambiguous term. And in fact, it was so ingrained in me that at the beginning, when I started talking, I thought, sure, there's no ambiguity here. And then I thought for a minute and said, oh, well, I guess it depends how you think about it. So let's see which way the author goes with it, and then we don't need to debate his view of life or just trying to get across the definition of the phrase, what is a statement? What does he think? He thinks it's unambiguous. He thinks it's definitely true or false, but not both. Yeah. So he thinks that large is a matter of opinion, a woman is not, and that is not a question we're going to resolve. So let me clear off these yeses and nos, because I don't know how you were thinking about it. But now the yes/no question is, do you get what's a statement? Do you get what would make the difference? If you think yes, put up your hand. Put up a yes or a no. I get some yeses. I get some no comments. I'll do another example here. More yeses are popping up, so okay, I don't think we have any concern. Now this last one, so this is weird language. I mean, if it depends on your opinion, what's large mean? Does this depend on your opinion, what's X? Oh, I think X is 5, so yeah, well. All right. Well, this is the one that our author calls an open statement. So it will be a statement after we fill in the value for X. See, does he want to call that a statement? And then when you answer homework questions, you answer it the way he did. You say, is that legit? Well, in introductory paragraphs like this in a math book, what the author's doing is making up the language that he will use to talk about things in the rest of the chapter. So it's a weird thing you get to do in math. You make up a word like statement, and it doesn't have to exactly match English. You just have to be consistent in how you use it. And then after you publish your paper, other mathematicians will avoid using the same word in a different way. They'll come up with a new word. So that's the way it goes. So what does he say? It's a statement because once you fill in the X, it's a statement. Okay. Are we good on that? So it's just when you do the homework and you see one of these, is it a statement? You say yes, because in his way of using the word, he means after you fill in all the variables. Okay. Questions? Looks like not. Okay. Let's see. Oh. Run down to another little historical thing. It talks about Lewis Carroll. Okay. George Boole. You can read those things. I don't have much independent knowledge to offer about those or to enhance it in any way, but it's kind of interesting to read. Okay. So simple statements and compound statements. Okay. So this is where you throw in words like and, or, not, if, then, if and only if, to take two statements and combine them together to make one bigger statement. Okay. And George Boole came up with these symbols. So I guess that's why our author uses the tilde, because Boole did. I like other symbols for that. We'll stick with the tilde for not. The upward wedge for and, the downward wedge for or. If P then Q, you use this arrow. And this is P if and only if Q. Now, let's see, where are points of confusion? Why are we not using the symbols that we had for set theory? Because it's almost the same thing. It's almost the same thing, but it's not the same thing. If you look here, P is not a set, it's a statement. I'll go to the store and I'm hungry. No, it's not sets. So it gets a different operator because it's a different thing. Now, a whole lot of what is true about set theory is also true in logic. There's a duality between the two theories. Okay. But it's not the same thing, and so it's different symbols. The one that is hardest for students to understand because of English, it's not the student's fault, it's a problem with English, this if-then. Because that's the language we use when we're trying to establish like a global rule, but that's not what this symbol is. It's like if it rains, I'll play cards. That's not saying always when it rains I play cards. Not saying whenever it rains I'll play cards. It's a one-off thing. The symbol here, the if-then, is just this one time. Okay. It's just saying this one time, you know, we're not going to have P without also Q. We're not going to have P and not Q. Write something on the piece of paper here. Get it where you can see everything. We just don't have P without Q. This time they go together. It means either we don't have P, or we got them both, P and Q.
Fred, we can't see what you're writing.
This is the last thing I wrote. TJ, are you able to see a P hat Q at the bottom?
I can see about half of that.
Oh, interesting. I got the whole thing on my screen. Well, let me figure out what I can. Did that do it?
Yeah.
Yeah. Oh, but now it's off the side.
Oh yeah, it is off to the side.
Okay.
All right.
All right. So I say, if it rains, I'll play then I'll play cards. Or I say, write it this way. If it rains an arrow, I'll play cards. I don't necessarily want to say then. Just means not rains without cards. Not forever, just we're checking it on one example. That'll be a little more clear when I do quantified statements. And I think instead of addressing your questions right now, the order that the activities come in for this section does this thing, the quantifiers, the for all, for every x, this, or there exists, or some x as this. If you do those activities on the quantifiers first, this arrow is going to become clear. I think rather than doing the back and forth on it right now, I want to use this as a heads up for what to watch for as you go through those activities. A little heads up that the arrow there is a one-time only thing, and you'll see what that means, the significance of that, when you do it in order, in the activities order, rather than the book order. Okay. Oh, let me scroll on down here. I forget these pages are so long. Okay, so anyway, you've got the meaning of negation. You want to say today is Friday and you negate that, today is not Friday. So here's your first example of a truth table. P is a statement. P could be either true or false because it's a statement. So it's one or the other. If P is true, then not P is false. If P is false, then not P is true. Whatever the statement may be, that's the way it works. That's all there is to that. So, Ellie Goulding is an opera singer. The negation is Ellie Goulding is not an opera singer. Dog does not need to be fed. The negation of that is the dog does need to be fed. Okay. So there's negations. Let me see if you guys have questions up to here, because I'm thinking this is going to be fairly self-explanatory, but you may have a concern that I haven't thought of. So anybody with questions up to here? Doesn't look like it. Okay. So when you write statements in symbolic form, like today's Friday and it's raining, I mean, the first thing you have to do is define the symbols to stand for the statements. And so when you're answering questions in the activities or on the homework, you can't, what students always do is they write down, they look at A here and they write, okay, P hat Q, P and Q. But they never told me what P means and they never told me what Q means. And if the story is complicated, I have no idea. Okay? So you have to tell the reader, you have to set it up, you know, P is this statement. Q is this statement. Then you can write P and Q. Or you can write not Q and R. Okay. So let me write, I feel obligated, it's my professional duty to write one of these. I'm so tempted to just go on because I think it's clear maybe, but you know. So let's let me change the share here. Okay. So question B. Is not raining, so that's not Q. And R. Now, you don't need parentheses because there's an order of operations. You probably remember from your algebra class, when you're simplifying an expression, you do what's inside the parentheses. You take the inside of a parenthesis as one group and you simplify it like a separate problem. Then you look at that and you find the exponents and you do the exponents first, and then after they're done, multiplication and division in order from left to right. It's unfortunate, like the programming language Fortran, you know, back in the 70s had multiplication before division, but that's not the math way. They're at equal precedence and you just go across from left to right. And negation, making the negative of a number, is right there at the same level. And then addition and subtraction from left to right. Well, in logic, you've got parentheses. We don't have anything like an exponent, but you've got and is like multiplication. And the tilde, the negation of a logical statement, is at the same order of precedence like negation of a number.
Fred, we can't see that. Okay, that looks good now.
Thank you. See how for algebra, multiplication, division, and negation are at the same level? You go left to right. Same way in logic. They're at the same level, you go left to right. And then at a lower level, or is like plus. So when you look up here at this example, so you do the not Q, and once that's done, it's just not Q, then and R. You see, so that if you write this symbolic way, it's not raining, that's one thing, and I'm going to a movie. Okay. So that's different from if you want to interfere with the order of operations, you use the parentheses to do it. So, all right. So, man, I wish I could see your faces. See like one face, two faces. Okay, thank you. Anyhow, let's do the yes/no thing. Do you feel okay with everything up to here? Looking for a yes/no in the participants window. Okay, I got 2 yeses, 3 yeses, 4 yeses, 5 yeses. Okay. And I always wonder, the people who didn't say anything, well, you didn't say no. I always wonder, though, is it just that you don't want me to talk to you?
They need to add a maybe button sometimes.
Yeah, that's legit, you know. Yeah. Yeah, it sort of makes sense. You're pretty sure you've got it, but you always wonder, you know, is there some other tricky aspect to it? Which, if I could think of any, I'd tell you. But the exercises, the homeworks, you know, they're pretty much designed to like bring out any particular issue that there might be. So, example 4 just goes the opposite way, where instead of, in the previous one, they gave you the statement and you wrote the expression. And here, they give you the expression and you write it down in English. So, like A here, Q, and P. Let's see, the game will be shown on CBS, and the game will be played in Atlanta. All right. So you just literally write those words down, and that's the way you answer that kind of question. These can almost be machine graded if, you know, try not to mess with the wording. You know, if you literally take the 2 sentences just the way they come and stick the and in between, you know, then it could be machine graded. I'm going to look at them, but, well, anyhow. Yeah, if you mess with the wording at all, you're likely to change the meaning. So, now, this statement. All men are created equal. Okay. I believe it, and I think our author is taking that to be not an opinion. Okay. Let's do all multiples of 2 or even. That way. So. Okay. I'm going to write this as a quantified statement. So let M be the set of all multiples of 2. Yeah, I know it's the same set, sort of just by definition, but I just want to illustrate the notation. I got a new symbol, an upside down A. So that means for each. The element symbol is belonging to for each X belonging to M, X belongs to E. Or I could write it with an if then. For each X belonging to the natural numbers, X being in M implies that X is in E. For each X, you don't have this without that. So let's see the difference. Up here, I'm stating a general rule because of the for every symbol, the for each symbol. But down here, it's just a one-off thing. I don't know what X is, but I'm only saying it about X. I'm saying it about this one particular number that we don't have this without that. Here I'm saying it's good for all numbers. See the difference? This is for one specific number. I just haven't filled in which one. This up top is saying it for all numbers. Somebody want to ask something about that? I feel like it needs to be discussed, but if I make speeches, I'll just repeat myself. Sure would like to hear from a real person to go back and forth on it. No? Well, maybe it's good. For all natural numbers X, if X is in M, then it's in E. That's different from just saying there's this number where if it's in M, it's in E. All this is just saying for this particular number, we don't have that it's in M without being in E. Okay. It doesn't matter that they're maybe both true or that M and E are the same by definition. None of that matters. It's just what is the what's in the notation. What are the two statements saying? It's different. Okay. So grouping symbols, they're showing you, let me change the share here. Yeah, so they have some examples where they show you how to use parentheses. I kind of did that, making the analogy for you. You read what they say too. It's, okay. So here's an English sentence. Oh boy, that's barely English. P and Q or not R. So English does not use the parentheses this way. Although when I'm explaining math to students and writing in English, I stick parentheses in there all the time, even though it's bad grammar, because it's the only way I know to make it really clear. But the way English sort of does it officially is with a comma. P, pause, and Q or not R. So you have to look for the comma to figure out where the parentheses go. So I was going to write, but yeah, you see how this is P and Q. You'd put it in parentheses, P hat Q, wedge R. Because the comma makes the P and Q stick together. So when you read these, just pause, forever between the, when you see a comma, just really pause. If P and not Q, then R or S. Okay. So Let's do this one. P hat Q, arrow R. Oh, when I did my order of operations, I didn't put the arrow in there because as far as I can tell, everybody uses the parentheses to make it unambiguous. But it would come later than all the rest. So P hat Q implies R. That in English would be you get a promotion and you complete the training. And because that's in parentheses, I put a comma. Then R, what? You will receive a bonus. So that was question A. We good on that? Okay. Now you can read through their examples and try to, you'll know if you got it. If you check your progress, it'll tell you if you're right, and then you'll know you got it. And then negation. So you read this, but I'll just kind of cut to the way you negate in English, like say all X's are Y's. The negation is some of them are not. Okay, or say no X's are Y's, then some of them are. And so all X's are Y's. The way you negate that is you say some X's are not Y's. It's the same table up here. It's just made the same table again, but in a more compact way. Okay. And the book and also the worksheets do this in English, at first at least. I want to show you how to do it in symbols. And then we'll be done. Okay. So here's, for every x belonging to the natural numbers, x is a real number. The negation of that. It's false, but that doesn't matter. We can still write the negation. I can negate it by just putting the not symbol in front. But that's the same as saying some natural numbers, there exists a natural number that's not an element of R. So the new symbol there is there exists x belonging to the natural numbers where x is not a real number. For all x's in the natural numbers, x is real. The negation is there exists x in the natural numbers where x is not real. Okay. But these ones are just done in English, and there's an activity, one of these worksheets by Lily Lum, which I edited a little bit. No airports are open. The negation of that is some airports are open. I'll leave those to you. I think as far as the going through the chapter is concerned, that's it. And I won't get into the excursion today, too much for one day. You won't come to it for a while in the homework. But that's the 3.1 overview. And I'm going to turn off the recording, see if anybody has questions.